All right, welcome back everyone to our seminar series on fractional calculus. Today's speaker is Fatma Al-Musalhi, an Omani mathematician who studied at Sultan Qaboos University between 2006 and 2017 for her bachelor's, master's, and PhD. She has worked in the same university since then, firstly at the Center of Preparatory Studies from 2019 to 2022, where she was awarded Best Researcher, and then as a full faculty member of the Department of Mathematics since 2023. Her research interests are in fractional differential equations and mathematical modeling of infectious diseases. She has published more than 10 research papers in index journals and presented at international conferences in Bulgaria, Finland, etc. She also serves as a peer reviewer for several high-level journals, and today she is going to speak to us about solving variable coefficients fractional differential equations. Please, the floor is yours.
Okay, thank you. Thank you, Arran, for giving me this chance and present my talk here. So I'll talk about solving fractional differential equations involving variable coefficients. Okay, here is the outline of my talk. First, I'll talk about fractional differential equations. Then the main results will be related to two methods for solving fractional differential equations involving variable coefficients. First method, it is based on fixed point theorem and successive iteration method. And second problem, it will be for second problem, I'm going to use a transmutation relation for solving the equation. Then I will give examples for each method here, and then I will end up with conclusion. Fractional differential equations are differential equations of arbitrary order. They have gained a considerable importance due to their applications in different areas in control theory, signal processing, viscoelasticity, and diffusion process. As you know, if we start with fractional differential equation with the constant coefficients, these equations can be solved by various methods like Laplace transform, series solutions, and operational calculus. Fractional differential equations with constant coefficients are generally easier to solve than the equations with variable coefficients because these variable coefficients will introduce additional complexity for the equations, and it will require different methods and techniques for finding the solution. Here I list some methods for solving fractional differential equations with variable coefficients. So in the literature, there are some methods it was used for solving this kind of equation. So first one is transmutation method, and it was used by Kyriakov and Sakabi in 1997. They used this method for solving fractional differential equation involving elyi-Kober derivative, okay? And there is also series method, okay? It was also used by Kilmick and Dizmowski in 2009. Operational method, it was used also it was used by Lushko and his co-authors. There are other people who used also operational method. Successive iteration and is also it was used by Fernandez and his co-authors, and also other people if we can find it in the literature. Here just I give examples for some references here. Numerical method, it was used by Change in 2018 for solving a fractional differential equation with variable coefficients. So if anyone interested for looking at these methods, maybe at the end once you see the references. The aim of this talk is to present explicit solution for non-homogeneous fractional differential equation with variable coefficients. So I will consider two equations. First equation is non-homogeneous equation for involving elyi-Kober derivative with variable or with continuous variable coefficients. Second problem, I will consider a non-homogeneous fractional differential equation involving weighted fractional derivative with respect to function. For the first problem, I will use fixed point theorem and successive approximation method. For the second problem, I will use transmutation relation. We'll start with the fractional operators that we need here in the talk. So here is the well-known fractional operators, Riemann-Liouville fraction integral, Riemann-Liouville fractional derivative and Riemann-Liouville and Caboto fractional derivative. I think all of you know this. I need also to recall elyi-Kober fractional integral. Okay, so elyi-Kober has 3 parameters here, and it is given by this integral. If gamma is 0 and beta is equal to 1, it will be reduced to Riemann-Liouville integrals times this power function. Also, I need to recall elyi-Kober fractional derivative, okay? And it is given by this form, so it will be the derivatives here times or of the integrals, okay? The normal way for the Riemann. So this one is elyi-Kober in the elyi-Kober fraction derivative in Riemann sense. Again, for gamma is 0 and beta equal to 1, this derivative, elyi-Kober derivative, it will be reduced to Riemann-Liouville derivative and times some power function. Okay, here is the problem. So here's our problem, non-homogeneous fraction differential equation with variable coefficients. So we consider multi-derivatives here, okay, of order delta 0 and delta I. And these orders has this relation. Okay. Now this differential equation, okay, it can be written in this form using the properties of elyi-Kober derivative. And we consider these initial conditions, okay? I don't know, maybe, okay. Here is the conditions down, so you can see the conditions for the parameters and for the variable coefficients here. We consider it to be a continuous functions. Okay, we'll move to the first method for solving the previous problem. Okay, so we'll use a new analytic method, and this analytic method it was used for linear fraction differential equation with variable coefficient. Okay, in last few years from some researchers in North Korea and then Kazakhstan and North Cyprus. So there are some references, okay? You can look at this method and how they use this method. But the idea for this method, it is based on fixed point theorem and successive iteration method. So first since we have non-homogeneous fraction differential equation with general coefficients, we are going to divide it to 3 steps. So first, I will find the solution for non-homogeneous fraction differential equation with 0 initial condition, okay? So in this case, we'll get the non-homogeneous solution or the what we call particular solution. Then we'll find the solution for homogeneous fraction differential equation with general conditions. And actually, for finding the solution of the second problem here, it will be depending on the first one. So if we are going to use the result of the first part. Then at the end, we are going to find the general case, the solution for the general equation, non-homogeneous fraction differential equation with general initial condition. So for first part, we are going to get the particular solution or non-homogeneous solution. For the second part, we'll get the homogeneous solution. And using superposition principle, we can get the general solution. So for the first equation, which is the non-homogeneous fraction differential equation with 0 initial conditions, we are going to follow the steps. And as I said, it is based on Banach fixed point theorem and successive iteration. So first step, we are going to rewrite the fraction differential equation as equivalent integral equation. Okay. Second step, we show that this equation corresponds to find a fixed point of the certain integral operator. So we are going to find the fixed point for the integral operator. Number 3, we are going to use a fixed point theorem. So to prove that this integral operator is a contractive mapping under suitable norm. 4, as a result of Banach fixed point theorem, we get a convergence sequence. So we are going to construct a sequence of functions which converge uniformly to the unique solution. And then rewrite the limit of the sequence as uniformly convergent series of functions. So here is our problem. Okay, we have the fraction differential equation. Using this substitution, okay, we are going to have integral equation. So this fraction differential equation is equivalent to this integral equation. So u is equal to derivative of this term. Okay, so using this substitution, we are going to convert or to reduce the fractional derivative to integral equation. And we can go back by using this substitution. Okay, so we can move from integral equation back to fraction differential equation using this substitution. So y here, if y is a solution for the initial value problem, then u is a solution for the integral equation and vice versa. Okay? So there is equivalence relation between the differential equation and the integral equation using these two substitutions. Now we need to define our integral operator. So we define our integral operator T lambda, and it is from C alpha to C alpha. Okay, so this space is defined as here. You can see the space here, which is a Banach fixed, a Banach space, sorry, under this norm. Okay, and this one is the integral operator that we are going to use. Okay. Now we use this estimate, okay, for lambda bigger than 0, okay, and these conditions for the parameters. So we need these estimates to prove the contractive mapping. There's a lot of details here, but I skip all the details. I'll give you just the main idea that this norm is less than some constant times the norm of u1 minus u2. So we need this k to make it very small here. So for this case, we are going to assume lambda is large enough to get the norm very small here. Okay, so by assuming lambda is a large positive constant to guarantee the contractive mapping here. So if it is contractive mapping, then using Banach fixed point theorem, the integral equation has a unique fixed point, and hence the fraction differential equation with homogeneous condition has a unique solution, u, which is given in this space. Sorry, y, which is given in this space, because u is a integral is a fixed point for the integral equation, then this will imply that y of t will be solution for the differential equation. Now, as a result, the limits of sequence un converge to ut, where the sequence is given by the following here. So f of t, which is the right-hand side, will be the initial iteration, and then un will be given by this integral equation. Then we can write it back to y of t, because our aim is to find the solution for the differential equation. So we use the previous substitution here. So we just do replacement, okay, or substitution. So we get the sequence in this form in terms of y of n. Now to construct the solution, we are going to do the iterations. So we start with y1, okay. Then we can end up with this, okay, summation. Then we get the second iteration, and one can continue, and then at the end you can get the clear nth iteration. So we can get a general form, which is yn. And as n goes to infinity, the limit will give the solution y of t. So here is the solution, and you have here multiple integral because it is power k. Okay, here is the main result for the first part. Okay, so this one is the theorem for non-homogeneous equation with 0 conditions. Okay, so if we assume that these conditions are satisfied and y of t belongs to this space, okay, then the fraction differential equation under these conditions has a unique solution, and it is convergence infinite, given by a convergent infinite series, where the infinite series is uniformly convergence. Now for the second part, as I mentioned before, we are going to use the result of this theorem. How? Because for second part, we are going to consider the homogeneous differential equation with general initial condition. So we are going to transform that equation to non-homogeneous problem with 0 condition, and then we can use this result. Okay, so as you see, this result is only for non-homogeneous part, or what we call usually particular solution. Okay, so for doing that, we need to recall elyi-Kober derivative of power function. So if we recall elyi-Kober derivative for this power function, we get 0, while for this derivative, for this power function, we get it 0, because here we find elyi-Kober of order delta 0 and here delta I. So we'll use this idea to rewrite our homogeneous differential equation. So for this part, we are going to subtract y. We are going to subtract the power function. And we know that the elyi-Kober derivative of delta 0 for this part will be 0. While for delta I, we need to add and subtract this power function because it will not give us 0. Okay. And then next, we are going to do substitution. Okay, so this part will be just, we can assume it to be Wj. Okay. So our differential equation, which was homogeneous differential equation, becomes non-homogeneous differential equation with the right-hand side, which is given by this summation. Okay. For the initial condition, it was general initial condition. We reduce it to 0 initial conditions. Again, there are a lot of details, so I just give you the initial conditions here, which are 0. So we make sure they are 0 conditions to use that theorem. Now, the solution of the above problem or initial value problem, it will be given by this form using the previous theorem, where the right-hand side will be this series. Now, y of g, okay, we can use back the substitution here to get the solution, the general solution, and hence we get this result. I think here there is plus sign. I forget to put plus sign. So here is the result for homogeneous equation with the general condition. So we use the idea of the previous theorem. I think here I missed to write plus. So this solution, which is yj, which is the when j equals 0, 1 till n 0 minus 1. So we get here the homogeneous solution, which is uniformly convergence, because we use the previous result. Now, by principle of superposition, we can guarantee that y1, y2 till yn 0 are a solution for the differential equation, and we can get also the general solution for non-homogeneous equation with general initial condition. So the solution for general initial value problem, which is given on this space, is given by this formula, where there is a multiple integrals here. So there is a solution for the first part here for f of t, it is the solution for non-homogeneous part, and the second one for the homogeneous part, plus this summation. Okay. Now to check from this solution, we try to consider some examples and check them with the literature. So first case, we put gamma equal to 0 and beta equal to 1. Then in this case, the fractional differential equation with elyi-Kober will be reduced to Riemann differential equation with Riemann derivative. So as you see, if we consider multi-derivative again, so this part will be just reduced to Riemann-Liouville derivative, and we get this problem, okay? And we use the theorem, okay? We use the theorem. By using the theorem, we get this series solution. This result is consistent with the results found by Arran and his co-authors, okay? So our results here is the same like the one which is in the literature. For constant case, if we consider another example where this variable coefficient is constant and we consider the order, or if we consider only one derivative, the equation becomes like this, which is a differential equation with elyi-Kober, but here there is some power function. Again, applying the theorem, okay, we get this series solution, okay? But this solution can be simplified, so one can simplify it and just do some iterations. We get this general formula, okay? So we get the solution in terms of Mehta function. This results coincides with the results, okay, found by Kiryakov and Sakhabi in 1997, okay? Now we are going to move to second method, okay, using transmutation relation. Actually, this method, it was used before, as I said, by Kiryakov and Sakhabi for solving the previous problem, which is elyi-Kober derivative, okay, with the differential equation involving elyi-Kober derivative. And what is the idea of transmutation relation? The transmutation relation, it is like you connect the more general operators with the classical one, like Riemann-Liouville derivative and Caboto derivative. That's what we are going to do here. Okay. So the method here, by using the method, we are going to transform our equation to which involve variable coefficients. And for this problem, I'm going to consider weighted fraction derivative with respect to function. And using the relation, we are going to convert it to fraction differential equation involving classical Caboto derivative. Then we are going to use the result, which is found by Arran, okay, and his co-authors, to write the solution in series form in terms of Riemann-Liouville integral. Arran and his co-authors, they used the same method that I used for finding the solution for fraction differential equation with the elyi-Kober derivative. It is based on fixed point theorem and successive iteration method. Okay. So here is his result. Just I want to put the results because we are going to use it here for this problem. So they consider multi-term derivatives involving Caboto derivative, and their solution are given on this form. Okay, and this solution is uniformly convergent series. Okay. Before we start with the problem, I need to recall the definition of weighted fractional operator with respect to function. So here is a weighted fraction integral with respect to function. So here is the function phi and the weight, which is W. And also we recall weighted fractional derivatives in Riemann sense and Caboto sense. Okay. Now, as a special cases for weighted fraction derivative with respect to function, if phi is equal to t, and the weight is exponential function, then the operators will be just reduced to tempered fractional operators, which are given on this form. Okay, so here is the tempered integral and tempered derivatives and Riemann-Liouville sense and Caboto sense. Other special case, if phi of t is a logarithmic function and the weight is power function, then it will be reduced to Hadamard-type fractional operators, which are given on this form. Okay, now I will write the transmutation relation for these operators. So as you see here, this one is the Riemann-Liouville integral. Okay, we can write it with some weight W and function phi here. So as you see, we write it in terms of Riemann-Liouville, the classical Riemann-Liouville. The same idea for Riemann-Liouville derivative and Caboto derivatives. Using the transmutation relation, we write them in terms of the original or the classical operators, Riemann-Liouville derivative and Caboto derivative. Now, what is M here and Q? W is the multiplication operator. So MW, if you apply it to the function, it will be the weight times the function, where Q phi is the functional operator of right composition. So if we apply Q to the function F, it will be F composed with this function. So I can show you one for, I think, for the first one, okay? So we are going to do these operations to get the left-hand side here. Just we'll go through it quickly. So first we'll apply the weighted operator, then the inverse of the composition, then the integral till you get this one. So here is some, here's how you apply the transmutation relation to get the weighted Riemann-Liouville fraction integral with respect to function. So first we apply the weighted operator. So it will be WF. Then we apply the inverse, and then we apply the integral. So we get this one. Then we do substitution to the integral. Okay. And after that, we apply the composition operator and then the inverse. And at the end, we get this weighted fraction integral with respect to function. So we connect the idea of transmutation relation, that we connect between the general operators and the classical one. So here is the problem. We consider this fraction differential equation involving multi-term of weighted fraction derivatives with respect to function phi with the variable coefficients here. Okay, and here is the initial conditions related to this derivative. Now here we are going to rewrite the differential equation. We start with the method of solution. So we rewrite the derivatives using the transmutation relation for the first derivative and for the multi-term derivative here. Okay. Now, in order to solve the equation, we need to get rid from these two, because I need the derivative, the classical derivative. I know the derivative of, I know the solution for fraction derivative involving Qaboos derivatives. So I need to get from the inverse operator of weight and the composition. So first we'll apply the weighted operator to both sides, and then the inverse of the composition to both sides. So by applying that, we get this equation, okay? And then if we do substitution, okay, if we do this substitution, so if we assume that this one is big Y and the right-hand side is just big F, we can replace it and we get this equation. We need to do this also for the initial conditions. So if we assume that S inverse is given by this, so if we apply to the initial conditions, okay, I write them just shortly here to make it easier for you to understand the operations, okay, and at the end we get the classical derivative here, okay, where J is integer from 0 to n0 minus 1. So by converting, or we convert the fraction differential equation with weighted fraction operator with respect to function, we convert it to differential equation involving the classical derivative, which is Qaboos derivative here, so as you see. And we get also the classical condition. So now we are going to use the results, which is done by Arran and his co-authors, as I showed you before, okay? Then the solution will be given on this form. And then we'll do substitution back and we get y of t at this form. Okay? And here is the, just summarize for the result as a main theorem. I did not write here the spaces because the space here was not enough, and I need maybe more time for explaining the idea of spaces, how we convert them, but if anyone interested, we can talk about this later. Okay, so here is the problem with this initial condition. It has a unique solution given by this form. Again, there is multiple here, okay? Now we need to see examples. Okay, so first example, I consider fraction differential equation with temporal fractional derivative, because temporal is just special case for weighted with respect to function. Okay, so if we assume that the variable coefficients is power function, okay, and if we assume also that the order is alpha between 0 and 1, so we get this fractional differential equation with temporal or Qaboos temporal fractional derivative. Using the theorem, we get this solution, okay? And as you see, we need to, I think we can simplify the solutions. Again, I skip the details here. So we get this solution. For the homogeneous part, we get the solution is as the weight times the Mehta function of 3 parameters, as you see here. And for the non-homogeneous part, we get this solution. So the kth integral here, we get only one integral, and it is in terms of g function, which is g or major g functions. And there is a weight here. So this one is the simplified solution for Qaboos or temporal derivative here. We give another example, fraction differential equation with Hadamard fractional derivative. And in this case, I consider homogeneous equation. So if we assume that the coefficients, the variable coefficients is given by logarithmic function here, okay? So we use the result again of our theorem. So the solution can be written on this form. And then simplifying, our solution is written on this form, okay? Where this one is again Mehta function of 3 parameters. So now we come with the conclusion here. We study two problems. So we study fraction differential equation involving elyi-Kober derivative with continuous variable coefficients. So the method of solution, it was based on Banach fixed point theorem, which gives us existence and uniqueness of solution. And then we use successive iteration or approximation method to get the explicit series of solution, which is uniformly convergent series. Then we study the second problem, which is fraction differential equation involving weighted fractional derivative with respect to function with continuous variable coefficients. And we use, in this case, transmutation relation. So we transform fraction differential equation involving these operators into classical fraction derivative, whose solutions are already known in the literature. Thank you for your attention, and here is some of the references. So first reference here, if you are interested for the first problem, it is a joint work with Arran. So if you are interested to look at more details, you can look at the first reference. For the other references, they are about fraction differential equations involving variable coefficients. So here, where the authors here, they use different methods for solving the equations. And here is also other references, okay? So that's it. That's my talk. Thank you for your attention.
Thank you very much for the presentation. Do we have any questions from the audience? You can either raise your hand or you can simply unmute yourself and ask. Rafshan, yes?
Yeah, first of all, thank you very much for a very interesting talk. I don't know you have seen or not, Michael Różański has published two papers where he investigated similar question. I mean, the same type of equations with Riemann-Liouville derivative, but inverse problem of finding right-hand side. So I've seen these papers published in Archive, but I don't know whether he published already in papers. Do you know these papers, Fatima?
No, I didn't see.
Okay.
But it will be good to see the idea for
the idea. You see, he's also using some type of Banach fixed point theorem. But the thing is that the equation has this variable coefficients with elliptic part and also right-hand side also. And he's considering this in Hilbert space. And the main question is to solve inverse problem. But to solve inverse problem, he first solves forward problem also.
Okay.
So
I worked with inverse problem, but maybe I didn't see this paper. Okay,
so
maybe
it was published in Archive 2023. Maybe it is already somewhere published. I think so. Okay, thank you very much. Anyway, very interesting talk.
Thank you for your comments. Thank you.
Thank you, Rafshan. Any other questions or comments? If not, then again, thank you very much, Fatma. I will stop the recording here.